203. So before starting the discussion, I want you guys to rate the entire contest on a scale of 10 so that we can improve the upcoming problem set. And also just quickly write a +1 if I am audible and equally visible. Write a +1 as a confirmation from your side so that we can start the discussion. Yes, Hemant, all the problem were really very nice, especially the last problem where we need to use the Robin Karp algorithm for a consistent hashing. So yes, this template seems good to me. So the first problem, which is named as a greedy customer, in this problem, a customer visit a fruit seller who has a collection of fruits and each with the specific price listed in the price array, where price of I represent the cost of the ith fruit, and the seller offers several purchase deal represented by a 2D array options of size q, which is defined by the pair of integer, that is q of I will contain two integers, meaning if the customer purchase x fruit, he will get y of them for free. And for every query, you need to calculate the sum of the cost of y cheapest free foods from the x fruit purchase for each option, right? And we need to return the total maximum possible sum of all the result. So basically for all the queries. So for the first test case, this is the price array, and we have two queries. So basically, if you purchase a three fruit, then what you will get? You will get two of them for free, right? And which two I will select? I will select the two which has the least cost, right? So here it is clearly mentioned in the problem statement, that is for each query, calculate the sum of y cheapest food from x fruit purchase option. So here we purchase the fruit which has the maximum price. We purchase the three fruit which has the maximum price, and then out of these three fruit, we will get two of them for free, which has the minimum value. So 30 plus 25. Then for the second query, we purchase all the four fruit, and we will get three of them, which has the minimum value. So that is a 30 plus 10 plus a 25, which is equals to 65. So 55 plus a 65, which is equals to 120. So now coming to the next example. So here in this case, there's a price array and the first query where we need to purchase the four items, and we get two items for free. So here we purchase the four item. So we pick the four item which has the minimum value, sorry, which has the maximum value. That is this is 60, 40, then 50 and 30. So out of these four values, we get two of them for free, which has the minimum value. That is 30 plus 40, right? It is equals to 70. So now coming to the solution, but let me explain and complete this explanation. So here we purchase a three fruit which has the maximum value. So that is a 60, 40 and 30, and we will get all three of them. So it is actually 60, 40 and 50, which is equals to 150. Then we purchase the two fruit which has the maximum value, that is a 60 and a 50, and out of which we will get one of them for free, which has the minimum cost. So that is this 50. So in total for all the queries, it is 270. So let's see how we can solve this problem. So the idea is very simple. First, I need to sort the array. So basically, we have a price array. We have this price array. Let me write some values here. So for example, let's say 30, then 20, 50, and let's say 10 and 25. So the very first thing, the very first step, we need to sort this array so that we get the values in a particular order. So sort this price array. And then for every query, we pick the maximum value. So for every query x comma y, so let's say queries of I, it is equals to 3 comma 2. 3 comma 2. So the very first thing, we sort this array. So after sorting, what will be my my new price array? So it is equals to 10, 20, then 25, 30, and 50. So then after we select these three values, these three maximum value, right? And we will get two of them for free. So we're definitely going to select these two. So for this query, what I will add? I will add this 25 plus 30 in my answer. So for this query, my answer is equals to 25 plus 30. And how we can calculate this thing? Because the size of the array can be up to 10 power 5. So we cannot iterate over the range. So that's why we use a prefix sum. So after this, create a prefix sum array. So we all know the trivial way to calculate the prefix sum. So prefix sum of I, it is equals to prefix sum of I minus 1. But in my implementation, how I implemented this thing, that is the prefix sum of I plus 1. It is equals to prefix sum of I and plus price of I. So in this way, we can calculate the prefix sum, and then we can easily answer the query in a constant time. And to answer the query, what will be my answer? Let me just quickly formalize this thing. So I am considering the one base indexing. So let me write this thing here. So index 0, not index 0, but index 1. So we have a prefix, we simply create a prefix sum array. So in my prefix sum, I calculate everything according to the one base indexing. So at index 0, we will store the value 0. Then here I will store 10, then 30, then 55, 30 plus 25, then 55 plus 30, which is equals to 85, and then 85 plus 50, which is equals to 135, right? So for a particular query, what will be my answer? So this is my index 0, then index 1, index 2, 3, index 4, and index 5. So the very first thing, I need to know this sum. So this sum will be stored at index n minus, let's call this value as x, and let's call this value as y. So this pink color range will store at index n minus x, n minus x. Okay, so let me check one thing. So n minus x plus y, and then out of this thing, I will just simply subtract the bigger values, right? So it is actually n minus x plus y. And then from here, I will just simply subtract n minus x. So in this way, we can calculate the answer result for all the queries. So here we have the implementation. First, I have taken the size of the array and the number of queries. Then initializing the answer with 0. And then here I sorted the array, then calculated the prefix sum. Then we can answer the query in a constant time, and finally I will return this answer. So the time complexity will be n log of n because of the sorting. So I hope it is clear to everyone. Write a quick +1 if it is clear to you, so that I can discuss the next problem. Now coming to the next problem of the contest, which is a water tank. It is also a pretty observation based problem. So you are given an integer array tank where tank of I represent the initial amount of water stored in the ith tank, and each tank has an unlimited capacity. Cool. But due to the municipal regulation, no tank can hold water more than X liter. This is the threshold. The maximum amount of water that any tank can hold, it is X unit. And you have an unlimited supply of a empty tank. This is very important. So try to pay more attention. You have an unlimited supply of empty tank available to store water. So basically, you can add as many empty tank as required, as you want, and you can transfer only whole integer amount of water between the tank. And during the transfer, if you transfer less than or equals to W liter of water, then all the transfer water will be wasted. And if you transfer more than W liters of water, only up to W liters of water will be wasted, and the remaining water will successfully transferred, right? And in this way, we need to maximize the total amount of water remaining across all the tanks, ensuring that no tank hold more than X liter of water. So now starting with the first example, 5, 7, 9, and 13. So here x is equals to 6. That is the upper limit for every tank. It is 6. No tank can store more than 6 unit of water. And whenever you transfer a water, which will be a whole integer, then y unit of water will be wasted. And if you transfer less than W unit of water, then all the water will be wasted. And if you transfer more than W unit of water, then W unit of water at most will be wasted, and rest of the water will successfully transfer. So what I can do? So here what I can do? One possible solution is to just simply transfer 1 unit of water from here. Just simply transfer 1 unit of water from this second tank. So 5, then 6, then 9, and 13. Right. So no matter wherever you transfer this 1 unit of water, it will definitely waste it. because it is less than the value of W. Then after, I will transfer 3 unit of water from this tank. I will transfer 3 unit of water from this third tank to the tank 1. And since the W unit of water will get wasted, so we will only get 1 unit of water. So it is a now 6 unit, it is also 6 unit, and it is a now 6 unit, right? Now from here, what I can do, now this is 13, and now I will select this last tank, and here we introduce one empty tank. We introduce one empty tank. So let's introduce an empty tank, which is holding 0 amount of water, 0 liters of water initially. And now we are going to transfer this the 8 unit of water from this fourth tank to the fifth one. So 13 minus 8, which is equals to 5. 13 minus 8, which is equals to 5. And now this value will become 6. So basically from 8, I need to subtract 2 because the 2 unit of water will get wasted. And now this is the best configuration that you can have. And out of here, now all the tanks has less than or equals to 6 liter of water, which is within the threshold. So my answer will be the sum of these values, which is 24 and plus 5, which is equals to 29. So this will be the expected output. And you can see here we have this at 29, right? Now one key observation here, it is never optimal. I'm not saying it is never optimal, but if you can achieve the answer in that way, then you can also achieve the answer in the new way, which I'm going to tell. So what I'm trying to say, it is always helpful to introduce a new tag, right? Because you might exceed the threshold. So what I'm trying to say, whenever you transfer, whenever you have selected this second, this a third tank, you have selected this a third tank, and you transfer 3 liter of water. So you transfer this a 3 liter of water from the third tank to the tank 1, right? But my claim is that no matter whichever tank you will select it as the destination, the 2 unit of water will always wasted, right? The 2 unit of water will always wasted, right? So this 3 minus 2 will be the amount of water that you will get. So why not? So why not it is optimal to introduce a new tank, right? Because now we are going to transfer this into an existing tank which already has some water, so you might exceed the threshold. So it's always better to introduce a new tank, right? And with this idea, now my new configuration will be just simply check now the idea here is to introduce a new tank every time. So it's an greedy problem. Introduce new empty tank every time. Now coming to the some casework. I iterate over all the tank, and just simply check one thing. If the tank value is less than or equals to the given threshold. So I can say this as case 1. So if tank of I, if it is less than or equals to x, so what will be my answer in that case? So in that case, I can just simply increment my answer by the value of this tank, right? Because it is within the threshold. So it is optimal to do not transfer any unit of water. Otherwise, the case 2, coming to the case 2, when the amount of water which is stored in the tank, it is greater than the threshold. So in that case, we have some extra amount of water, right? And it is equals to tank of I minus the threshold. This is the extra amount of water we have. For example, let's say we have a tank of I. It is equals to 25. It is equals to 25, and the value of x, it is equals to 6. So how much extra amount of water we have? So it is 25 minus 6, which is equals to 19. We have a 19 unit of water extra. Now every time we introduce a new tank, this will be my main idea. Every time I introduce a new tank, so what is the best way? So the best way to split this 19 into a chunks of 8. So that is 8, because the threshold here is a 6 unit, right? So basically in the first call, I will simply transfer 8 unit of water, right? In the second call, again I will transfer the 8 unit of water, and then we are left with a 3 unit of water. So it is not possible to again transfer the 8 unit of water. But why here we are transferring the 8 unit of water? So because we all know that if I transfer the 8 unit of water, 2 unit of water will get wasted, and eventually we will get the 6 unit of water, right? Which is nothing but the threshold. So that's the idea. Every time transfer x plus a w unit of water. So this will be the second observation. Every time try to transfer x plus w liter of water, right? So that this w unit of water will get wasted, and we reaches the threshold, that is the maximum amount of water that we can store in any tank. So every time we introduce a new tank and we transfer x plus a w unit of water, now how many times we can transfer? So let's call this value as a q. So it is equals to extra divided by this x plus w. These many times we can transfer the water completely. Now we are left with some remainder, and which is equals to extra mod x plus w. For example, in this case, the value of q, it is equals to it is equals to 19 divided by 8, which is equals to 2. So that is we can 2 times we can successfully transfer the water, and now we are left with some remainder. So remainder is equals to 19 mod 8. So 19 mod 8, which is equals to 3. So we are left with a 3 unit of water. Now this 3 unit of water we need to completely transfer, and from here we need to subtract a w. So what I can say here, this remaining water, from this remaining water I need to subtract a w, because w unit of water definitely be wasted. So answer plus equals to q multiplied by x, right? Because here the value of a q is equals to 2, and we introduce a new tank, add 6 unit of water, add, or I can say add x unit of water, again introduce a new tank, add x unit of water. So q multiplied by x, the number of time we can do this operation, and multiplied by the threshold. Now what about this remainder? So then again in my answer, what I will add remainder minus x, right? But there is an edge case. It might be possible when the remainder is 1, right? And the amount of water that will wasted, it is 2. So now if you find the value of remainder minus w, then it is equals to minus 1, right? So that's why we take the maximum of these two values, 0 comma maximum of 0 comma remainder minus x. So yeah, that's the complete solution. Just simply check for the case 1 and case 2. Now coming to the implementation. So just simply iterate over all the values, and this is my extra, which is equals to maximum of a 0 comma val minus x. It might be possible when the value is less than dx. So in that case, the extra unit of water that we have, it is 0, right? And in my answer, I simply add this value after subtracting this extra. And how we can manage this extra unit of water? So extra divided by x plus w, and then we add this factor, and this is my remainder, and maximum of 0 comma remainder minus w. So we'll answer all such query regarding the tips and technique to start or learn DSA after the end of after the discussion. So now hope it is clear to everyone. This solution takes a linear time, order of n, where n is the length of this array. Write a quick +1 if it is clear to you. So basically, it is mentioned in the problem statement, that is, whenever you transfer more than W liter of water will be wasted, right? And if you transfer less than the W unit of water, then all the amount of water will get wasted. So this is our case 2. Now coming to the third problem, minimize the special power. So you are given a connected undirected graph with n number of node and m number of edges, and among these k special node, among these k are special, basically k nodes are special, and each has a power associated with it, which is p. And whenever you visit a special node, your current power is updated to p, right? No matter whether you are having the lesser power or the higher power, always the power is updated to p. And for any node, you can move along the edges, basically the adjacent neighbor, and each move will cost you 1 unit of power. And your task is to start with the node 1 with the initial power p, and your power must be never become negative in between. That is, power should be always greater than or equal to 0. And the goal is to determine the minimum possible value of a p that allow you to reach at node n from the starting node 1. And the initial unit of power that we have, it is p, right? And if it is not possible to reach at node 1, then in that case return -1. So let me just give you an example. And this is really very interesting problem. So let's say we have a node with the value 1, and let's say it is connected with a node with the value 2, and let's say then we have a 3. So let's consider this graph. I can introduce some other edges, and let's say we have a 7. And out of these 7 nodes, let's say some of the nodes are special. So for example, this node 3, let's say this node 3 is a special node, and also let's say this node 7, let's say this node 7 is a special node. So basically the starting node, this is my source node, source vertex, this node 1, and here the power is p, the initial power is p, and this is my destination node where we want to reach, right? So basically every wherever you take a move from one node to its neighbor, it will cost you 1 unit of power, right? So from here, what I can say, I need to tell the minimum value of p. And whenever you reaches to the special node, your power will always reset to p, and your initial power is also p. And we need to minimize this value of p to reach at a node n successfully without having a power 0 in between. So we need to find the minimum value of p. Cool. So let's start with the p is equals to 1. So let's say p is equals to 1. So whenever I start with the p is equals to 1, then whenever I reaches to this node 4, then my power becomes 0, right? Or if I reach to this node 2, then also my power becomes 0, right? And whenever I reaches to this node 3, my power become -1, and -1 is not possible. So that's why p is equals to 1 cannot be your answer. So let's say p is equals to 2. So what if p is equals to 2? So if p is equals to 1, and if I follow this path from 1 to 4, now here the power is 1, and whenever I follow this path from 4 to 3, now the power is 0, and since it is a special node, so it will be converted to 2. Now the power is 2, and from here I can follow this path. Now the power is 1, and whenever from the 6 you take a path to a node 7, now your power becomes 0, right? And now we have reached to the destination node 7, right? And this is the minimum unit of power that we require. The minimum value of p, it is equals to 2. So 2 will be my answer. Now if you notice one thing, then this problem has a monotonic search space. This problem is having monotonic nature. So monotonic predicate nature. And if the problem is having monotonic predicate nature, then you can simply apply a binary search. This is the necessary and sufficient condition to apply a binary search. So basically what I'm trying to say, if p is equals to 2, if it is possible to reach at the destination node without having a power negative in between, then it is also possible to reach at the destination node for p is equals to 3. For p is equals to 4, there also exists a path, and if it is not possible to reach at p is equals to 1, then it is also not possible to reach at p is equals to 0, right? So isn't it a monotonic predicate nature? So if my function return true for this value, so it will return true for all the values of p which is greater than or equals to 2, and it will return me false for all the values of p which is less than 2, right? So yes, it has a monotonic predicate nature with one critical point, and we are interested to find this critical point. So this will be my answer. The minimum value for which my function returns true. This will be my answer. Now the next thing, how we write the check function. In my binary search, we must have a check function, that is this function which return true or false. Now for this thing, we can apply the Dijkstra algorithm with some little modification. So the value of a mid, let's just first find the value of low. So the value of low, it is equals to 0. Because it might be possible when you have only one node in the graph. So if you have only one node, then your source and destination both are same. So in that case, you are already at the destination node, so you don't require any initial power, right? So this is the maximum value of your answer, and the value of high, it is equals to n, the maximum value. It might be possible when we have a skewed tree. So for example, let's say we have a node 1, we have a node 1, or actually it is n minus 1, but let it be. Then node 2, then node 3, and up to node n. So let's consider this graph. So if we have a graph with a n number of node, so how many edges that we require to visit? So the number of edges that we require to visit, it is n minus 1. So the maximum possible answer that you can have is n minus 1. Now simply apply the binary search. So that simple template for a binary search, while low is less than or equals to high, we simply call a check function, but before that we find the value of a mid. So it is equals to low plus high divided by 2, low plus high and divided by 2, right? And this mid is nothing but your check function. This mid is nothing but your decided power. So simply now complete this check function. So which takes one integer. Let's call this an integer p. So now I decided to make the power as p. And now we need to check. Now we need to check whether it is possible to reach to the destination by having the value of a p, this arbitrary value of p. So for example, let's say the value of mid. Let's say the value of a mid. It is equals to 3. It is equals to 3. So now the value of a p, it is equals to 3. So the initial power is 3. From here, I can follow this path from 1 to 4, then from 4 to 3, then 3 to 6, and 6 to 7. So with in this way, we can reach to the destination node. And this is nothing but simply apply the Dijkstra algorithm. Dijkstra algorithm. And I'm not going to explain how to use the Dijkstra algorithm. And this was the prerequisite for this problem. Now coming to the implementation. So here I have created a graph. Then we have this unordered set. Is special. And initially I'm going to fill all the values of this vector, so that in a logarithmic time or in a constant time, because we have an unordered set, in a constant time I can check whether the node is special or not. Then value of low, high, and answer. So I'm going to initialize the answer with the -1. Then find the value of a mid. Then call the check function. Update the answer if it is returning true, and also update the value of high and low. And finally, I will return this answer. Now coming to this check function. So this time we are not going to use the Dijkstra algorithm directly, but instead we modified this thing. So here we have a best array. In a trivial Dijkstra algorithm, we have a distance array where distance of u simply store the minimum amount of minimum weight, or I can say minimum cost that is required to reach at node u. But I'm going to modify this definition. Best of u will simply store the maximum remaining power which we can have at node u. So let me write this thing. In a trivial Dijkstra algorithm, we have a distance array. So distance of u, or I can say best of u, both has the same meaning. So distance of u will simply store minimum cost required to pay to reach at node u, right? But in this time we are going to modify this thing. So this time distance of u, or I can say the best of u, both are the same thing, will store the maximum unit of power we can have at node u, right? And because as much as power we have at a particular node, as long as distance we can cover. So the higher the power is, the maximum the distance you can cover. So that's why here we have the term maximum, right? And in a trivial binary search, we use a min heap. But this time we are going to use the max heap. And yes, that's the complete solution. For every node, let me write the step. That is remove the node, remove the pair with the maximum value, with the maximum power. Then explore all its neighbor from the queue, priority queue, I can say. Then explore all the neighbor and update the neighbor or I can say relax the neighbor if it is updatable. And how to check whether the neighbor is updatable or not? They simply check the current power and plus one, not plus one but minus one. Current power minus one, and if it is greater than what we have stored at stored previously, then update it. Update the neighbor and also push the neighbor in your priority queue. This is a simple modified Dijkstra algorithm. So here we have the array best, and consider one base indexing. Initially fill all the values with the minus one, and the initial power at node one, it is a p unit. Then this is my priority queue. In the priority queue, just simply push the value p comma 1, and every time we remove the pair with the maximum power, and this is the node corresponding to it. And if it is not, if we already had the better result in my best array, then continue with this node. And if it is a special node, then power will be updated with p. And if we got our desired node, then we simply return true. Otherwise, iterate all of its neighbor. Then the next unit of power that we are left with is the remaining minus one, because if we travel one through one edge, then the power will reduce by one. So remaining minus one. And if it is greater than zero and better than what we have stored, then update the neighbor and also push the neighbor in a priority queue. So that's the complete solution. The time complexity will be same as the time complexity of a Dijkstra algorithm multiplied by the time complexity of this while loop, which is log of n. So yeah, that's the complete solution for the third problem. Now coming to the last problem of the contest. Longest disjoint substring. So you are given a string s consisting of a lowercase letters. You are also given an integer k, and your task is to find the length of the longest substring of s such that there are at least k disjoint occurrences of string s, and a substring in s. And a substring is a continuous sequence of a character within the string. And here we have the definition of a disjoint occurrence. So let me explain you with an example. So let's say we have a string geeks for geeks, and let's say the value of k, it is equals to 2. So what is the length of the longest substring which has k disjoint occurrences? So if I consider this string geeks, so consider the substring geeks. So here we have one occurrence of geeks, and this is another occurrence of geeks. So how many occurrences we have? So we have a two occurrences of this thing, which is greater than or equals to k. So yes, it is valid. So it is valid, right? It is valid. And what is the length? What would be the length of this substring? It is equals to 5. Its length is equals to 5. Now the thing is, this problem also has a monotonic predicate nature. This problem also has a monotonic predicate nature. So if the substring of length 5 is possible, then the substring of length 4 is also possible. So this is a universal true. If the substring of length 5 is valid, then the substring of length 4 is also valid. So consider the substring of length 4, which is this one, geek. So it also has a 2 occurrences greater than or equals to k. So yes, it is also valid. So you can consider any substring of length 4 within this one, the bigger one. Now the substring of length 3, it is also valid. So consider GEE. So this one is also valid. Now consider the substring of length 2. So yes, it is also valid. So what I'm trying to say, if the substring of length 5 is valid, if the substring of length 5 is valid, then the substring of length 4 is valid, the substring of length 3 is also valid, substring of length 2 is also possible, and the substring of length 1 is also possible. So if your function is returning true for here, for this 5, then it will also return true for here, 4, true for 4, and true for this 2, right? And if it is false for 6 length substring, then it is also false for a 7 length substring. So in this way, it is false for all the integers greater than or equals greater than 5. So this problem also has a monotonic predicate nature, so we can simply apply a binary search. Now what will be the value of low? So the value of low, it is equal to 0. It might be possible when all the characters are having frequency less than k. So in that case, your answer will be 0. Now the value of high. What are the maximum length of the substring we can have? It is nothing but n divided by k. The maximum amount of chunk we can have, disjoint chunk of length k we can have, it is n by k. Now write a check function. How we write a check function? So coming to the check function for a particular value of mid, it return you the boolean value. So let's consider the substring geeks for geeks, and n is the length of the substring. Now the length of the substring can be up to 10 power 5. Length of the substring can be up to 10 power 5. So you cannot write it over all the substring. It is not possible. So what we can do? So the idea here is to use the consistent hashing, which is a rolling hash, which is the prerequisite for this problem. So if you do not know what is a rolling hash, then I recommend you to just go and watch some video or read some article for the rolling hash, which is a Robin Korf algorithm. So we are going to use a hash. So let me give you a general idea for the hash. So let's say we have a two string s1 and s2. Now you need to check whether these two strings are equal or not. So one possible way is to iterate over the character by character. The second possible method is to generate the integer corresponding to the string. So that is, I will write a some mathematical function, that is a hash function, and will pass the integer here s1 and use the same hash function and pass the string s2. Now if both the string give you the same integer, give you the same key, or I can say if both the hash function give you the same value, then I can say s1 and s2 both are same, right? And these values are of integer data type. So now this time we don't have to compare each and every character. We only have to compare two integer, and to compare the integer, we can compare two integer in a constant time. So that's the idea of a hash function. Now the next thing, which hash function we can use. So there exists a lot of hash function, but a popular family of a hash function, it is a polynomial hash. So we are going to use a polynomial hash. Now coming to the polynomial hash function. So let's say you have a string with the character s1, s2, s3, then s4, and up to s of n. Now this polynomial hash function will simply return you the integer value s1. So when basically we map every character to an integer, and the best is to use the sky value. That is a, if the character, let's say s of I, if it is equals to the character a, so I am going to consider this a as the integer 1. We consider the string b, sorry, character b as the integer 2, and up to character z as the integer 26. It is not optimal to start with a 0 because it has some edge cases. Let me just give you an example. So for example, let's say you have this thing. So now here if you start with a 0, so now it is a 0 plus 0 multiplied by some factor, whatever you decided to multiply. Let's call this as a lambda. So 0 multiplied by something which is equal to 0. So the hash value is 0. Now let's consider the string with only one character. So it is equal to 0 if you start with a 0. Now in both the cases you get the same value, but both these strings are not same. So yes, it has some probability of a failure. It has some large number of collisions. That's why we start with 1. So the hash function will be s1 plus s2 multiplied by p. And what is this p? This p is a prime number. This p is a prime number. And s3 multiplied by p square, then s of 4 multiplied by p power 5, and up to, sorry, s of 4 multiplied by p power 3, increasing power of p, and s of n multiplied by p power n minus 1. This is my polynomial hash function. Now the next thing is how we can calculate the hash value efficiently. So to calculate the hash value efficiently, we are going to use a Horner method. So Horner method is nothing but very similar to the prefix, or I can say the suffix sum. With the help of a prefix and suffix sum, we can calculate the value of a hash value of the substring in a linear time. So this is called as a Horner method. So it simply says that declare a suffix array. So instead of calling this as a suffix, I'm going to use a lowercase letter h. So do not confuse with the notation. So h of I will simply store p multiplied by, or I can write it this way, s of I, the character which is at index I, and plus p multiplied by h of I plus 1. And this h of I plus 1 value we already know. So that's why we iterate from the bigger values of I to the smaller values of I. So this is my suffix of I can say. And one another important thing, this value might be very large. So every time we take a mod with some integer. So do not forget to take a mod with some integer m. And this m is also a prime number, which is of a 9 digit, just to have the minimum number of collisions. Cool. So initialize the value of index n plus 1 with 0. So h of n plus 1, it is equals to 0. Then iterate over the integers from n to 1. Considering 1 base indexing, so iterate over the integer from n to 1, right? So the value of h of n plus 1, it is equals to 0, and it is a kind of a base case. Then the value of h of n, just keep this formula in your mind. I'm using this formula. So it is equals to s of n minus s of n and plus p multiplied by h of I plus 1, which is equals to 0. So p multiplied by 0. Then h of n minus 1. So it is equals to s of n minus 1 plus p multiplied by s of n. Then h of n minus 2. It is equals to s of n minus 2 plus p multiplied by s of n minus 1 plus p square multiplied by s of n, right? And so on up to h of 1. So h of 1 will simply store s of 1 plus p multiplied by s of 2 plus 3 p square multiplied by s of 3 and up to p power n minus 1 multiplied by s of n, which is same as this thing. So what I'm trying to say, this h of I will simply store the value of hash value of a substring which is starting with the index I and up to index n. So s of I, then s of I plus 1 and up to s of n. So h of I will store this information. Now this is a Horner method, and it is very similar to the suffix sum, and do not get confused. Every time we take a mod with m just to compress the answer. Cool. Now the next thing, how we can find the this can be done time. So this one will take a linear time, order of n. Now the thing is how we can find the hash value of a particular substring. So consider the substring which is consider a substring from I to j. So now the most important formula. So consider the substring from index I to index j, and you need to find the hash value. So this can be given by the formula h of I then minus p power the length of the substring, which is j minus I plus 1 and multiplied by h power, sorry, multiplied by h of j plus 1 and take a mod with n. So after the pre-computation, just simply use the formula to find the hash value of a substring from I to j. So let me just give you a quick proof of this formula. So what this h of I will store? So h of I has simply stored s of I plus s of I plus 1 multiplied by p, s of I plus 2 multiplied by p square and up to s of n multiplied by p power n minus I. Then what h of j will store? H of j plus 1 has stored. So it has simply stored, or also I can write it this way. So we have an index j. So s of j, it is equals to p power j minus I. then plus s of j plus 1. It is stored p power j minus I plus 1 and up to s of n multiplied by p power n minus I. So this value has stored in h of I, index I of array h. Now h of j plus 1, what this has stored? So this has stored s of j plus 1 multiplied by p power 0, which is equals to 1, plus h of s of j plus 2 multiplied by p plus s of j plus 3 multiplied by p square, right? And so on up to s of n multiplied by p power j minus 1, p power j minus 1. Now if you have noticed one thing, now coming to this formula, coming to this above formula, now if you have noticed one thing, if from here, if from h of I, if you simply subtract the value of if you simply subtract the value of h of j plus 1, then it will not give you the desired value, right? Because here we have some extra power of p. For example, the expected power of p here, it is 0. But here what we have, here we have, sorry, expected power of p, here in this case expected power of p, yes, it is 0, it is 0. But here what we have, here we have a j minus I plus 1. Now if you notice one thing, after this, let me write for s of j plus 2. So s of j plus 2, so it is equals to p power j minus I plus 1 and again plus 1, right? And if you simply write for s of j plus 3, then it is a s of j plus 3 multiplied by p power j minus I plus 1 and plus 3. So what I'm trying to say, we have this extra power of p, which is j minus I plus 1. And even if you expand this here, then it is equals to, even if you expand this thing here, then it can also be written as in this way. That is a that is n minus j plus j minus I and plus 1. This can also be written in this way, right? So that's why we have this extra value of j minus I plus 1. So that's what we need to subtract from here. Cool. So with this idea, we can use this formula, and this formula will simply give you the value of s of I multiplied by p power 0 plus s of I plus 1 multiplied by p power 1 plus s of I plus 2 multiplied by p power 2 plus s of I plus 3 multiplied by p power 3 and so on, s of j multiplied by p power j minus I, This is same as the desired hash value of the substring. And with this formula, we can calculate the hash value in a constant time. So this will take order of n time. So the pre-computation take linear time, and in a constant time, you can find the hash value of a substring. Now let's see, we got a hash value of a substring. How we compare? So let's consider the substring as a geeks for geeks. So index is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now let's consider the value of a mid. It is equals to 5. So what I'm going to do, I'm going to find the hash value of all the substring of length 5. So starting with the index 0, starting with the index 1, and so on. So from here, we will get some hash value. Let's call this as a k1. Then starting with the index 1, some another hash value. Let's call this as a k2. From index 0, sorry, from index 1 to index 5. Then from index 2 to index from index 2 to index 6. This value is k3, right? And whenever you consider the substring of length 5 starting with the index 8, then you will get the same value, which is k1, right? Now the next thing is that now the next thing, we need to check for the disjoint set or not. We need to check whether the intervals are disjoint or not. So for this thing, we are going to store the indexes, right? So just simply create a map. Just simply create a map of integer and vector. So here you store the hash value, or I can say keys. Store the hash value and keys, and at here store the indexes. Store the indices, right? So basically, corresponding to key k1, we have a two index, that is index 0 and index 8. Now simply check one thing, whether this value, that is whether the intervals are overlapping or not. You know the length of the interval. So 0 plus 5, 0 plus 5 minus 1. This is the length of the first interval. So this is your first interval starting with the index 0, and the last index of this interval, it is 0 plus 5 minus 1, right? Then the second interval is starting with the index 8, and the last index of this interval, it would be 8 plus 5 minus 1, because both the indexes are inclusive. So 8 plus 5, 13, and 13 minus 5, 12. So this is from 0 to 4, and this is from 8 to 12. So simply compare the last index of the interval of the previous interval. So let's call this value as a last. And if this value is less than the starting index of the new interval, then both the intervals are disjoint. So increment the value of count. Right? And if the value of a count is greater than or equals to k, then return true. That is, yes, this value of a mid is possible. It is valid. So that's the complete solution. And if it is sounds confusing, then what you can do, you can revisit to this lecture, then take a multiple pause, and especially for this a hash function, and yeah, this formula, it is very, very important and very useful as well. So make sure to use it for the future problem wherever you require the hatching. Now coming to the implementation. So yeah, this is the method that I need to complete. Taken the size of the string, then if the value of k is 1, then return the value of n. If the number of disjoint intervals that required it is 1, then we can consider the entire string, right? And here I'm going to use a double hashing just for a lesser probability of failure. Because if I use the double hashing, then it has very less probability of failure. So more chances, more likely to get the correct answer. But again, the probability can never be 0. The probability of failure can never be 0. But we can minimize it by using the double hashing or triple hashing. So this is my power, and here I'm going to use this variable base, and it is same as the variable p in my explanation. Then these are the two values of mod. You can also change this value p with some smaller prime number. Let's call this as a 31. Now here I pre-calculate this value, that is pre-calculate the value of a power p1, p2, p3, p4, p5, and so on. Then this is my suffix. This is for the suffix hash. So they simply calculate the suffix. And this is the lambda function, how you can get the hash value of a particular substring from L to R. So this is simply my Horner method formula. And once I get the hash value with the help of both the two hash function, then I need to combine both the two hash function. So I'm going to use the OR method, and this is really very popular among the competitive programmers So make sure to remember this logic, how we can combine the two hash values, right? Just to minimize the number of collision. So shift every bit to the left, basically 32 bits to the left. Now we have a 32 positions, and then just simply add all the values of the another hash, value, all the values of the another hash function. Cool. This is my binary search, simple binary search logic. And if for the particular value of mid, if it is returning me true, then update the value of low, and finally I will return the value of low. Now this is my check function. If the value of L is 0, then always return true. Then this is my unordered map. As per the discussion, use the map, and here I will store the hash value, and then I will store the index cell. So just simply get the hash, just call the lambda function, and this lambda function will return you the hash value of a string, substring from L to R. So just simply find the hash value of a substring is starting with the index I, and it is having of length L, or I can say mid. Now simply push the index corresponding to the hash value. Then I iterate over all the unique hash value, and I iterate over all the index cells, initializing the count with 1. And this is my last index of the first interval. Then every time check whether it is possible to update the value of count or not. If the starting index is greater than or equals to greater than the last index of the previous interval, then increment the value of count and also update the value of last, because this is now my active interval. And once the value of count at any time becomes greater than or equals to k, then return true. That is, yes, it is possible. So in this way we can solve this problem. Now the time complexity is n log of n base 2. So yeah, that's the complete solution. And if you have any better solution, then you can just simply post your solution in the comment box. So yeah, that's all for this session. Thank you everyone for watching this session, and have a good day. Good night.